So once the devices are ready, so we have to inspect the devices under the microscope. Then it would be sent to the dicing section. The dicing section, the devices would be cut into kits. The wafer would be cut into kits, that is in each device. Once we have the device, it would be sent for packaging. So here you have to put the MEMS device along the microelectronic device or microprocessor, etc. This process is known as packaging. So once that packaging is done, then your device is ready for the final testing or experimentation. So normally, as we discussed, that you would need wafer for the fabrication of microelectronics and MEMS devices. And normally, in most of the occasions, we are using silicon wafer. Silicon, as compared to germanium and gallium arsenide wafers, silicon wafers are cheap and they are widely available. But in comparison to glass wafers are low cost. But as we discussed, that glass is an insulator material. So depending upon whether you want to fabricate your device on an insulator material, if that is the requirement, then you have to buy a glass wafer. Otherwise, you have to buy the silicon wafer. Silicon wafers are normally made. Silicon is abundantly available. We discussed silicon is abundantly available in sand. Sand is actually silicon dioxide. Sand is silicon dioxide, and sand is available abundantly throughout the world. So one of the reasons that why silicon is used for the microelectronics and MEMS is that sand is abundantly available, which is actually the raw material for the silicon wafer. So normally we take the raw material, it is melted, we melt, and we have silicon, melted silicon, and then actually from the melted silicon ingot is made. We would study how silicon ingots are made in more detail. And there are two processing technologies by which the silicon ingots are made. One is known as stone FZ technology, and the other is the Chernovsky technology, which is known by CZ technique. These two are used to make the silicon ingot. And when we have the silicon ingot, we have to cut the silicon ingot into silicon wafers. And once we have silicon wafers, these silicon wafers need to be polished. So mechanical polishing of wafers, normally known as CMP. So the polishing is done so that we have a mirror surface. Silicon wafer has a mirror surface. In order to have a mirror surface, so that polishing is done. Here you see different types of silicon wafer, and here you see the marking. These cut marks represent the direction. Here you see that it is written that P type. So first, when you are buying a wafer, you have to first you need to know whether the wafer is N type or P type, or whether you need N type wafer or P type wafer. So initially, when you are buying, the first question should be that I need N type or P type silicon wafer. Once that is decided, then on top layer, what plane should be on the top layer? What plane must make the top layer of silicon wafer? As here you see that 111, which means that this top surface of the whole wafer is made of this plane 111. So this is P type 111 silicon wafer. And the other side, this cutting side, this plate side represents another plane, and this plane is 110 plane. Orientation of this plate, this orientation of this plate represents plane 110 plane. Similarly, here you see N-type silicon wafer, and the top surface is made of 111 plane, and the plate represents, this plate represents 110 plane. This is P-type silicon wafer, and the top surface is made of 100 plane, and the plate, this plate represents 110 plane. Here this is N-type 100 silicon wafer, and the plate represents 110 plane. So before actually buying the wafer, you have to decide whether you need N-type silicon wafer, P-type silicon wafer, 100 silicon wafer, 111 silicon wafer, single crystal silicon wafer, polysilicon wafer, silicon on insulator wafer, etc. So, and size, which diameter you need, and thickness, they are available in a variety of thicknesses and variety of diameters. So before the fabrication, you have to decide about all those things. So normally MEMS use preliminary integrated circuit type fabrication, allows batch fabrication. We do batch fabrication because the microfabrication or microelectronic fabrication is very expensive process, and the cost of the devices have been reduced with the help of the mass production based fabrication. Batch fabrication means on a single wafer, we have to produce thousands of tiny devices in a single run. So on a single wafer, we have to produce thousands of devices in a single run. So, and then we have to cut those into each device or chips. So by that way, we could reduce the cost of the device. And by batch fabrication, we have tremendously reduced the cost of the fabrication of MEMS devices and microelectronics. Because in my market, you could see that a single wafer is few dollars. It is $2, $1. So we have tremendously reduced the cost of the fabrication of microelectronics and MEMS with the batch fabrication technique. Also, we are using other integration techniques such as direct sensor, processor integration, and actuator integration. Normally, there are two techniques by which we combine the MEMS device with the relevant electronic circuitry. One is the monolithic approach. The monolithic approach, you have to produce the MEMS device along the relevant electronic device. This is known as monolithic approach. And in the hybrid approach, what we do, we separately produce the MEMS device, and we separately produce the relevant micro electric circuit, and then we combine these in the package of the device. That is known as hybrid techniques. So both techniques are widely used to fabricate the complete sensor or actuator. So this slide is about that monolithic approach. In the monolithic approach, we fabricate the MEMS device along the relevant electrical circuit on the same chip. So this is known as monolithic approach. In the monolithic approach, we do this. So here you see that this is a MEMS device and relevant electrical circuit, and they are made, fabricated together on the same chip. So this is the monolithic approach. one fabrication process for both IC, integrated circuit, and MEMS. So this is monolithic approach. In the hybrid approach, we have to separately fabricate the sensor or actuating MEMS device, and we have to separately fabricate the relevant electrical circuit, and then we have to combine these in the package. So that is the hybrid approach. Remember that micro machining is not 3D. It is micro machining is a surface fabrication technology. We add layer surfaces to the top of the substrate, and we add layer by layer, and layer by layer we make the device. So it is not a 3D technology. Although we are working or we are coming with the technology so that we could fabricate the MEMS and NAND with the 3D technology, still work is going on in that. So micro machining is not 3D, while a large variety of structures are possible. Arbitrary 3D structures are difficult to fabricate. Here they are just trying to show you that since the MEMS technology is a surface manufacturing technology, still we could use it to make 3D shapes or structures. Here you could see that using the planar technology. Using this planar technology, we have made a 3D mechanism of structure. So normally, as we discussed, that we have to fabricate the MEMS layer by layer. So we have to deposit thin film on top of the silicon wafers. So this process is known as thin film deposition or film formation. Film formation, thin film deposition or formation is less than 5 micrometer. Thick film deposition is around about 50 micrometer or less than 50 micrometer. Thermal oxidation, wet or dry. In thermal oxidation, what we do, we make or fabricate a thin layer of silicon dioxide on top of the silicon wafer. The process is known as thermal oxidation. The enhancement of the transformation of silicon into silicon dioxide. Consumption ratio 0.44 silicon to silicon dioxide. Silicon dioxide that is made would be amorphous, thin film, conformal coating. Okay, so normally how to make thin film on top of the silicon wafer, and if we want that this thin film should be silicon dioxide, so we have to heat the silicon wafer inside the furnace in the presence of oxygen. So silicon wafer is heated inside the furnace in the presence of oxygen, and when it is heated, silicon combines with oxygen, and a layer of silicon dioxide is formed on top of the silicon wafer. If you use oxygen gas, then it would be dry thermal oxidation. But instead of oxygen gas, if we use water vapor, if water vapor is used, then it would be called wet thermal oxidation. The film of silicon dioxide, which would be formed on top of the silicon wafer, it would be amorphous. And normally this process, that is this deposition process inside the furnace, would take place at 1000 to 1200 degrees C at atmospheric pressure, and hours of deposition time, depending upon how thick you want, how thick silicon dioxide layer you want on the silicon wafer. So if you want thick layer, so for a longer time you have to put the silicon wafer inside the furnace, you have to heat inside the furnace. If you want thin layer, then for less time you have to put it inside the silicon wafer, inside the furnace. And normally these silicon dioxide layers on top of silicon wafers are used as a passivation layer, sacrificial layer, arc edge, diffusion mask, or as a insulation layer, etc. Other techniques by which you could add the layers are the chemical wafer deposition, CVD. CVD stands for chemical vapor deposition. So a chemical process would take place on top of the silicon wafer, and a layer of material would be formed on the silicon wafer. So in chemical vapor deposition, we have low pressure chemical vapor deposition, metal oxide chemical vapor deposition, plasma enhanced chemical vapor deposition. So these different CVD processes are available. The nucleation of gases species on substrate to form a substrate. So on top of we would supply a variety of gases depending upon which layer you want on the substrate, and those gases would react with the silicon wafer, and a layer of a material would be formed on top of the silicon wafer. By that way, we could make polycrystalline or amorphous thin films with conformal coating. The process would take place at 600 degrees centigrade, lower than atmospheric pressure, one order of 1 micrometer per hour deposition rate. This is the deposition rate. So in 1 hour, 1 micrometer thin layer would be made. So normally, meaning that if you perform that process for 1 hour, the layer that would be formed on top of the silicon wafer would be 1 micrometer. For 2 hours, 2 micrometers. And normally these this layer could be used as a structural layer, passivation layer, fabrication layer, art as diffusion mask or insulation layer. Some materials that you could deposit by PVD, these materials could be silicon dioxide layer, silicon nitride layer, polysilicon layer, PSG, phosphosilicate, silicate, phosphosilicate glass, which is known as PSG. So these materials you could add to the silicon wafer with chemical wafer deposition. Other thin film deposition processes, which are the physical processes, one of it is evaporation. In the evaporation, what we do, we put the wafer on top, and the metal which you want to deposit, it is put in the crucible, and that crucible is heated. So the metal actually melts and then it evaporates. It flows in the upward direction. And here on top, here we have the silicon wafer, and that metal actually settle down on the silicon wafer, and it condenses on the silicon wafer, and a thin film of material is formed on the wafer. This process is known as evaporation. The operation of metals by resistive, inductive, or electron beam heating in order for condensation to occur on a substrate, thereby forming a film. The film that would be formed, it would be amorphous, semi-conformal coating. The process from melting temperature of metals to 200 degrees centigrade. The temperature for this process depends upon which material you want to deposit on top of the silicon wafer. And you have to heat the material up to the melting point, 200 above the melting point, and the process would take place in a high vacuum. We would study this process in more detail. I'm just going through the introduction. And the process would take place under a high vacuum. And normally the deposition rate in this process is 2 micrometer per hour. And these deposition which is done by operation are used as metal conductor lines, solder deposition, mirror surfaces, electrical contacts, etc. Other deposition processes, sputtering, electroplating, and spin coating. Sputtering the physical removal of atoms from a target material by energized ion, plasma, and reformation of films on the substrate. So we use a plasma to remove the material from the target, and that material is then it then flows and actually settles down and condenses on the substrate, and a thin film is formed. Thin films, these thin films would be amorphous, conformal and non-conformal coating process would take under high vacuum. Most materials can be sputtered. Those could be metals, organic or inorganic material, etc. Electroplating is the method by which we could add the material with the process of electroplating. So the electrochemical reaction of a solution on a sheet surface to form a metal film. It is amorphous, thick, and greater thin. So for thicker layer, normally we perform electroplating. Spin coating is also a technique by which we could add layers on top of the material. Thin film material dissolved in a volatile liquid solvent, spin coated onto a substrate to form films, but the quality would be not so good, low quality, but convenient amorphous thin or thick films. The process would take place at room temperature, that's approximately 100 degrees centigrade. For curing, we would heat the material and then we have to cure it at this temperature. The materials that could be spin coated, organic polymers and inorganic glass collectors. This is the sputtering machine by which we could perform sputtering. Doping, normally if you want to make your silicon wafer or some portion of the silicon wafer N-type or P-type, for that we have to add impurities inside the silicon or wafer. That impurities could be boron or phosphorus. Boron in silicon is for P-type and phosphorus in silicon is for N-type. Silicon or polysilicon doped for the purpose of increasing conductivity or creating H-stops, constant limited source diffusion or ion implantation. So normally two methods are used. One is the ion implantation by which we could add impurities within the silicon wafer or within some portion of the silicon wafer. And the other method is the diffusion. So here you see that the diffusion, in the diffusion, we have to expose the wafer to a gas which would have either boron or phosphorus atoms, and we have to keep this in a furnace at relatively high temperature. And those boron or phosphorus would actually diffuse inside the silicon wafer. So this process is known as diffusion. In ion plantation, we would have an electron beam gun, just like here, and we have to bombard the boron or phosphorus atoms on the portion where you want to add the impurities. So this is known as ion implantation. This is ion implantation and this is diffusion. I think it's sufficient for today. If you have questions in today's lecture, please ask. If there is any question?
Wait.
Hello?
No, sir.
क्वेश्चन नहीं है?
Yes, sir. It's Fahim. No question from here.
Is there any other question or discussion if you want to do it about it? नहीं है क्वेश्चन?
No, sir.
No, sir. Thank you.
Thank you, sir.
Okay, if there is no question, then I will finish the lecture. Thank you. Inshallah, फिर next class में मुलाकात होगी. Okay, अस्सलाम वालेकुम.
Okay. Walaikum assalam.